In order to predict P of the probability of y given a label x is the same as computing the value of P of x given y times P of y. Right? So we know from Bayes' rule that P of y given x is proportional to P of x given y times y. So that sets up the learning problem for naive Bayes. Instead of learning this probability directly, we learn these two probabilities. This is the first one. The first term there is the likelihood of seeing this feature vector when the label is y, when the label is say plus. And the second term is the prior probability of that feature vector of that label, of the label being y. For example, plus again. Any questions about? Yes.
So the only thing is we have so many feature vectors.
Right.
So this value is going to be very, very small.
Yes. Why do we care? Actually, will it be very small?
I mean,
This
we have so many examples.
Sure. Let's say the product is very small, but it still has to be normalized to 1, right? So when you say the actual value of P of y given x is P of x given y and y divided by the sum over all what?
Px.
It's basically P of x, but P of x is simply the sum over all labels y prime the denominator will make sure that even though the numerator might be a very small number, the denominator makes sure that these are reasonable probabilities. But the point is well taken. The probabilities might be very small. So what? It should not matter. It should not bother you too much. There's another interesting problem though. Because the feature vector x can be a large vector, it can be a high dimensional. So x can be, say, a million dimensional vector. Learning this P of x given y can be a nightmare because the number of possible values of million dimensional, even Boolean features is 2 power a million. So if you want to fill up a table for every possible x, we are not going to have enough data to fill up those probabilities. And what's the answer to that? The most simple answer that we know of is to make assumptions. The assumption that the naive Bayes classifier makes is that every feature is conditionally independent of all the other features given the label. So the naive Bayes assumption is simply P of x given y, here x is a vector, is the product over all the individual features, P of xi given y. So here x, the vector, is x1, x2, all the way to, let's say, we have d dimensions. So the naive Bayes assumption is a pretty strong independence assumption. It says that any two features are produced independently, exist independently of each other, given the label. And fact of life is this assumption is often violated. It's more often violated than it holds. And yet the naive Bayes classifier exists and it seems to work, which is an interesting something to think about. Now, the next thing that we started in the last lecture was how do you learn the naive Bayes classifier? In order to learn the naive Bayes classifier, you need to learn these two probabilities, P of x given y and P of y. But so here x is this vector here again. All the x's without subscripts are vectors. Now, P of x given y by the naive Bayes assumption is just this quantity here. So, effectively, learning the naive Bayes classifier is the same as learning these probability functions. So, to learn the naive Bayes classifier, I need to learn probability of y, that's the prior. And for every feature, xi, I need to learn the likelihood of that feature given the label. So for every feature, for every y. So if I give you some way of producing these probabilities, effectively you can make a prediction. If you have these probabilities, you can make a prediction. So the learning problem is learning these probability functions. And we started this procedure for, I started working through the estimation procedure for these probabilities. And how do you learn probabilistic classifiers in general? What are the criteria? What are the probabilistic criteria for learning?
Maximum probable.
Maximum a posteriori or maximum likelihood. You should know these terms.
Pure posterior.
In this case, we'll be looking through how to learn a naive-based classifier using the maximum likelihood setting. The maximum likelihood setting, let's go back. You're given a data set. Here xi is a vector, this xi is a vector. You're given a data set with feature vectors with labels. The usual thing that we have always. And the maximum likelihood estimate is simply the, okay, so and what do we want to learn? We want to learn all these probabilities, this entire thing here. Or let's call these probabilities, all of them together forms a hypothesis. So the hypothesis that we want to learn is simply the set of all these probabilities. And the way we do it is we find the hypothesis that maximizes the probability of the entire data set given the hypothesis. But this data set is simply a set of all these examples. So in some sense, again, to remind you, the idea of maximum likelihood learning is you're asking what is the set of probabilities that is most likely to have created this data set. This particular set of m examples that you see. And we assume that every example is independent, so the probability of the data set is simply, this term is exactly the same as the product over each individual example. And then we just work through the math. From here to here, we apply the naive Bayes assumption. So from here to here is just Bayes rule. And from here to here is just a naive Bayes assumption. We say that the prior still remains, and the likelihood is the product of individual features. The likelihood of seeing the vector x is simply the product of the probabilities of seeing each feature xi given the hypothesis. And in what might be probably like the standard way of going ahead, instead of maximizing probabilities, instead of doing any sort of arithmetic over probability or calculus over probabilities, we work with log probabilities because log probabilities tend to be easier beasts to handle. So you take the log. If you're maximizing, taking the log should not change the answer, or at least it should not change the R max. It will change the value of the max, but we don't care about that. It won't change the hypothesis that actually is the maximizer. So our goal now is to find the maximum of what is called the maximum of this function here. This function is also called the log likelihood function, right? Because this was the likelihood, and we took the log, so we are now maximizing the log likelihood. So the standard way of learning the naive Bayes classifier is to do maximum likelihood estimation, and invariably we end up with the problem of maximizing the log likelihood function. Let's look at this log likelihood function. We want to find the maximum of this value. We've come as far as we possibly could without making any functional assumptions. Without making any functional assumptions about the nature of these probabilities. So at this point we have to start thinking notice that so far I have not told you anything about what the xi's and the yi's look like. I have not made any assumptions about what probability distributions actually generate these things, what probability distributions are involved. I've just said, there are some probability distributions. At this point, we need to assume what probability distributions there are. So this is the modeling assumption. There are two levels of modeling assumptions here. The first one is the naive Bayes assumption. We assume that each feature exists independently, is conditionally independent of all other features given the label. The second one is the functional form of these probability distributions. Let's say that we are doing binary classification. So there are two labels, 0 and 1. And you can treat this as a coin toss, as a Bernoulli trial. Which means there's a coin, the prior probability, we care about P of y equals 1, the prior probability of P of y equals 1, let's say that it's P. With probability P, even before you see an example, the label is 1. The likelihood is somewhat more complex. Let's say that again all our features are also Boolean, which means all our features are also zeros and ones. We need to consider two cases. Remember, the likelihood is this term here, the class conditional feature likelihood. So we want something that says probability that some feature xj takes the value 1 when the label is something. We have two functions of this kind, and the label is 0 and we have probability of xj equals 1 when the label is 1. We don't have to worry about the probability of xj equals 0 because that's just 1 minus these terms. Right? Okay? Let's consider the case when the label y equals 1 first. We assume when the label is 1, the probability that xj equals 1 is a. It's a coin. So when the label is 1, for the jth feature, you toss a coin. You toss this coin whose bias is aj. If it says heads, you say 1. If it says tails, you say 0. The probability that it says heads is aj. So the way this is set up is each example is created in the following way. First, you toss the prior coin. You have a bunch of coins. First you toss a coin with whose bias is p. If that coin says heads, you have this entire collection of coins, all of them, let's call them A. You have D coins because you have D features. Each of them you toss once. If it says heads, the feature value is 1. If it says tails, the feature value is 0. You have D coins, you get a D-dimensional vector. On the other hand, if the coin at the top had said tails or 0, then you move to a completely different set of coins called B. There are D of them again, and you toss them all. And if the jth coin says heads, with probability Bj, then you say 1. If the jth coin says tails, you say 0. And that way you get D values and you get a D-dimensional feature vector. What I just described is the generative story of the naive Bayes model. The assumption in the naive Bayes model is with this kind of a thing is effectively that you have these collections of coins, and this is how the data is generated. Now, given a data set, the learning problem is to learn all the biases of these coins. So effectively, the hypothesis consists of this P, A, and the B. Because if you knew the values of P, A, and B, you basically can now predict what is the probability of the label for a new set of features. So the learning problem is just simply learning the values of P, A, and B. Before we go ahead, let's try to see if we can guess the values of these things. Suppose I give you 10 examples. In those 10 examples, 8 of them are labeled 1 and 2 of them are labeled 0. What's the value of P? 0.8. This is fairly trivial, right? I mean, there's nothing, it seems pretty obvious. If, let's say, among all the positive examples, among the 8 positive examples, feature number 1, so you have 8 examples. Feature number 1 among those 8 examples is 1 6 times. So what is A1?
6 by 6.
6 by 8, 0.75, so 3/4. right? So what's the learning algorithm? Let's just, so you have 10 examples. 8 times if the label is positive and 2 times the label is negative. And what you just told me is that the value of P here, 0.8. Okay? Among the 8 positive examples, x1 equals 1 6 times, which means the value of the probability of x1 equals 1 given that y equals plus is 0.6. Oh, sorry, is 6 by 8. Because there are 8 examples and 6 of them, the value is positive. So, what I just described here is the learning algorithm. Our goal is to learn these probabilities, and Naïve is one of the simplest, has probably the second simplest learning algorithm that I am aware of, which just says iterate over the training set and count. Yeah, I could invent that without doing too much thinking, but let's see if that makes sense. Because we have this principled way of designing learning algorithms, namely the maximum likelihood principle. Let's see what the maximum likelihood principle tells us. How do we learn? In order to get that working, we need to do a little bit of notational gymnastics. Let's first only worry about the prior. Let's say we want to learn the prior. Now I'm going to define. So in order to do that, I need to define this function p in terms of this function p of y given h in terms of this value p. In order to do that, I'm going to introduce this idea which we've not seen before called the indicator. The indicator is something fairly trivial. It's called the indicator function. It's also called the Iverson bracket. It's simply a function that takes a number. That takes a boolean z and returns a 1 or a minus, a 1 or a 0. So this function is simply defined as the value is 1 if z equals true, value is 0 if z equals false. We've seen this before, right? We've been using this abstraction all the time. This is the formal way of mapping true to 1 and false to 0. It's just called the indicator function. Using this indicator function, I can define the probability of y given h in the following way. Probability of y given h is the product of these two terms. It's p power the indicator that y is 1 times 1 minus p power the indicator that y is 0. Let's see what this means, because this seems rather tedious. Let's see what this actually means. So if I write at this font, can people at the end see? Good. Is this, what do we want to say? So by the way, just remember that h is the combination of the p, a1, a2, all the way to a, b, b1, all the way to b. It's this entire vector. So the probability of y given h is p if y equals true, or if y equals 1, and 1 minus p if y equals 0. That's just the definition. That's the model that we've assumed, because this is basically the definition of a coin toss. Now, when y equals 1, what is the value of this indicator? When y equals 1, the value of indicator for y equals 1 is 1. Right? Does that make sense? Yes.
I mean, if we compare it with the perceptron or SVM, then it should be greater than equal to 0.
What should be greater than equal to 0?
This just indicates the conditions, one of the conditions that we have.
No, this is the indicator is just a way of taking a boolean and converting it to 0 or 1. So So let's just, I feel like this is way too complicated for a simple idea. So let me try to simplify this. I'm defining P to be the probability of the Y, the label Y, given the hypothesis is P if Y equals 1, 1 minus P if Y equals 0. Okay? Now, I can equivalently write this as, it is P power, I claim that I can equivalently, this is equal to the P power, the indicator that Y equals 1, and 1 minus P power, the indicator that Y equals 0. Let's see why this is true. Case 1, Y equals 1. When Y equals 1, the indicator that Y equals 1 equals 1. The indicator that Y equals 0 is 0. What does that mean? It's asking, is Y, the term on the indicator on top is just asking, is the value of Y 1? If it is, then say 1. So the indicator of Z is 1 if Z equals true, and 0 if Z equals false. And by the way, I'm introducing this notation deliberately in order to actually prove this whole thing. I don't need to introduce indicators. It turns out that introducing the idea of an indicator makes it very easy for me to teach the expectation maximization algorithm coming up. So just bear with me here. If you think about it, you can actually derive the whole thing without using indicators. But indicator is just a way of asking, is this proposition true or false? If it is true, then give me a 1, otherwise give me a 0. The proposition here is Y equal to 1. If it is true, the indicator is 1. So what is P power indicator that Y equals 1? It's simply P. And 1 minus P power indicator that Y equals 0 is 1. So when P of Y equals 1, given the hypothesis, is simply the product of these two terms, which is the product of these two terms, which is P. Case 2, when Y equals 0, you should convince yourself that this term evaluates to 1 minus P. Why? Because the same thing, in the indicator that Y equals 1 is 0, the indicator that Y equals 0 is 1, P power 1, P power the indicator that 1 is 1 minus P. I take the product of those two things, you get 1 minus P. So this term here is just a compact way of writing this condition. You have this branched definition, this using indicators is just a compact way of writing the same sort of a multi-term definition. Did you have a question?
Yeah, so are we bringing this because we are having a log outside?
Yes, exactly right. We are bringing this kind of a power notation because eventually we have to take the log of this term. And when we take the log of this, the log of this product becomes indicator times log P. So what is log P of Y given H? It's simply the indicator that Y equals 1 times log P plus the indicator that Y. And this makes our calculus a lot easier. Questions? Alright, I'll go ahead assuming that everyone understands this. The nice thing about this is that we can write down I'm not going to explain this in too much detail. What I just did was to write down this term using an indicator because we have a log and this term is exactly the same as log, indicator that yi equals 1 times log p plus indicator that yi equals 0 log 1 minus p. It turns out that you can write the second term also using these indicators. And let's just very briefly think about this. The value of p of, again, value of p of x j equals 1 given y is, there are multiple cases here. Okay, when y equals 1 and xj equals 1, the value is aj. Because remember, this was the prior set 1, which means we move to the set of coins defined by a. We toss the jth coin in the a cluster, and if it says 1, then the value of xj is 1. So in fact, let's just remove this property of xj given y. But when y equals 1 and xj equals 0, meaning the jth coin set false, this is 1 minus aj. When y equals 0, we move to the entirely different set of coins. When y equals 0 and xj equals 1, this is bj, and then you have 1 minus. So you have these 4 cases. Now, in the previous thing, what we saw was we had a way of writing down this kind of a multi-way definition of a function using these indicator functions as a big product. I can do the same thing. Every condition here on the far side gets an indicator that y equals 1 and xj equals 1. So this is exactly the same as aj power the indicator that y equals 1 and xj equals 1 times 1 minus aj times power this indicator times 1 minus aj power an indicator for this. If you've not seen this before, this seems like just notation overload. Anyone agrees with me? Good. It turns out that this makes the next step basically trivial. I'm able to write down this thing. I can again take log of this big product and write down the log probability as a sum. We have a sum, we have sums of sums. Now I can take derivatives of this quantity with respect to each of the a's and the b's very easily. I can take the derivatives and set them to 0. Now here's the cool thing about these indicator functions. Let's say I have 3 things. Let's say I have, let's take the example that we had before. You have 10 examples, y1 through y10. You know what, 10 is too many for me to write. Let's say y1 through y5. 1, y2, y3, y4 and y5. Let's say y1 is 0, the rest of them are all 1. Okay, now think of what is the value of the indicator of what? This quantity. The sum of all the indicators that yi equals 0. This is simply the indicator that y1 equals 0 plus the indicator that y2 equals 0. y1 is actually 0, so this is 1. Everything else is not true, right? So really this is equal to 1. Similarly, the indicator that yi equals 1, the sum of all the i's is 4. So summing over indicators give you counts. The count function is simply sums over indicators. This may seem like either a very obvious thing or a very boring thing, but effectively what this does is taking the derivative of this quantity and setting it to 0 will give you many sums of indicators in both the numerator and the denominator, and what you get is exactly what you had expected. The prior probability, the probability that the label is 1, is simply it turns out the maximum likelihood estimate is you count the number of times the labels are 1 in the data set, divide by the number of times the labels are 1 plus the number of times the labels are 0. And all these counts show up because they are actually sums of indicators. Aj is the probability that the label is 1 when, the jth feature is 1 when the label is 1, is simply you count the number of times the jth feature is 1 and the label is 1, divide by the number of times the label is 1. This is exactly what you would expect, in fact what you guys told me when I asked you to informally come up with the answer with the 10 examples. And similarly, Bj is also what you expect. It's the count of number of times the label is 0 and the feature value is 1, divided by the number of times the label is 0. This is all there is to learning the naive Bayes classifier. All that derivation and stuff leads to this. So if you have to write the learning algorithm, it's literally just this. If your features are all Boolean and your labels are Boolean, here's the quote-unquote learning algorithm. The learning algorithm is iterate over the data set, keep track of all these counts, and then find the probabilities. And probably, so far at least, the simplest learning algorithm we've seen. Questions? In fact, I'm not even going to dignify this with an algorithm block, because I know how I'm not going to, it's just a for loop.
It appears more like an information game.
It looks like that because we are doing probabilities, but it's even simpler than that. But also remember, you remember that from the previous lecture, one of the interesting things about naive Bayes is the hypothesis space of naive Bayes is the set of linear classifiers. So effectively by doing these counts, you're learning a linear classifier. Other questions? Yes.
So if this is just learning a linear classifier, why not just do perceptron? What makes this better or worse?
Okay, good question. What makes this better is that this is trivial. I mean, imagine you have a data set that does not even fit in your hard disk. You want to learn the classifier, all you have to do is just stream through every feature and you get the counts. You could argue, yeah, you could have done that with perceptron as well. You don't have to, this is in some sense, this does not even require that kind of an iterative update strategy. There are no mistakes to check. It's what is called a count-based method. There is no, the learning algorithm is ridiculously simple to implement, and both also in terms of computation. You don't have to take dot products, you don't have to do anything, just count. So that's the plus. The minus is that in practice, this ends up tending to not perform as well as any of those other linear classifier algorithms you've seen. Because there are certain concepts. When I say concepts, I mean this in the way that we understand concepts to be, certain concept classes. Certain concepts that are linearly separable, and yet this process will not find the linear classifier. I should have probably put that one of those examples in your homework, but I have. It's not terribly hard to come up with a data set where it's easy to show that it's linearly separable, and yet this process will not find the classifier on the data. So the naive Bayes classifier learns a subset of linearly separable functions. So if you are pressed for time and if you are pressed for compute, maybe use this. But in general, probably I tend not to use the naive Bayes classifier. Okay, so let's just work through an example of what this is, because it's so simple I can actually work through an entire example. This is the tennis example that we saw before. You have 14 examples and 9 of them are labeled positive. So the prior probability, what we call P, is what we call P, is the probability that the label is plus. It's the number of times the label is plus divided by the number of examples, so it's 9/14. And the probability 1 minus P is simply 5/14. And let's say I want to calculate the likelihood of each feature separately because we are doing naive based. The probability of O equals S given that the label is plus is you count the number of times the label is plus, so you have 9 examples. This is not even the right way of. So the number of plus labels is 9, the number of times among those examples, the number of times the feature value is S is 2, so this likelihood is 2 nines. I can do the same for other feature values as well. So the likelihood that the outlook is rainy given that the label is plus is 3 nines because there are 3 such instances, and the outlook is overcast given that play is plus is 4 nines because that's all the possibilities. So these 3 should add up to 1. And you do this for all other possible attributes. Yes?
So the earlier derivations we did were for Boolean features.
That's right.
So here we have
Multi-class, which means that that's a very good observation. It means that the probability functions that you assume here are slightly different. Here we are assuming that instead of A and 1 minus A, we are assuming that this is let's just erase all this. Let's call this AS. Oh, no. A overcast equals S, A overcast equals R, and A overcast equals O, which should be equal to 1 minus AS minus AR. So this is our probability assumption. As an exercise to check if you understand this stuff, maybe you should try to derive these values with this assumption. Derive the fact that counting is a good idea. It is actually, but you might want to convince yourself that it works. That's a very good observation. Alright, so naive based classification, for any learning algorithm you need to define how learning works and how prediction works. For example, for the perceptron, learning works using the perceptron algorithm. The prediction works by taking the dot product and comparing to 0. In naive Bayes, learning is trivial. You just count how many times all these different events, all the different configurations occur, and you normalize them to get probabilities. It also, as we just saw, it generalizes to multi-class classification. Very trivial because it's just counting. Prediction is once you have the probabilities, you can either predict just the probabilities or you can find the label that is most probable and call that the prediction. So that's the easy part about. So in some sense, naive Bayes is a fairly trivial classifier to implement. I haven't asked you to implement the naive Bayes classifier in any of your homeworks, but if you're interested, I encourage you to try to do that, or maybe even for your project. Partly because it's so easy and it will give you an idea of how the naive Bayes classifier compares against any of the other learning algorithms that you tried in your data sets. Let's look at some practical issues with the naive Bayes classification. The first thing is that something that someone brought up, a concern that someone brought up in the last lecture. Yeah, the naive Bayes assumes that features are conditionally independent of each other. That's the naive Bayes assumption. Conditionally independent given the labels. But who says real life behaves this way? Maybe the features are not conditionally independent of each other, which means the entire edifice that we built up should be thrown out. Okay, that's definitely a valid concern. We'll talk about that. And then the second concern is actually more practical. We're doing this counting. What if a certain configuration never shows up in the data? What if a certain feature value is never false when the label is false? Would count of that configuration be 0? More importantly, should that probability be 0? How do we deal with it? Let's look at the first thing first. When the naive Bayes assumption is not satisfied, which means that the probability of the feature vector given the label, in other words, the likelihood, is not the product of each the product over all the features. If the naive, as I said earlier, if this in real life this assumption is almost never true, and yet for many interesting applications, naive-based classifiers kind of work well enough. They don't work. They might not be the state-of-the-art classifier, but they are surprisingly good, given how simple the classifier is. And there are many different ways to explain this. I'm not going to talk about that because it's not entirely clear to me that those explanations are exactly for this setting. Those explanations often require additional assumptions which may actually cripple them further. For example, one explanation is naive-based searches on this on a subset of linearly separable functions, and we know that linear classifiers are extremely powerful. We don't get all linear classifiers, but it seems that maybe this searches over a subset of linear classifiers that are good enough. It seems that is the keyword. Not clear that's true, but it appears to be. Alright. The second thing is that there might not be, what if there's not enough data to get reliable estimates of probabilities? So, suppose you never see this pair here. When play tennis is yes, let's say temperature was never cold. Just so happens in those 14 examples we collected, I don't remember if this is correct, but let's say this situation never happened. If you trivially follow the naive-based method, the maximum likelihood setup that we saw, this count is 0, so the probability is 0. So the probability of temperature being cold when play tennis is yes should be 0 if you just did the counts and came up to the probabilities. But is that a good idea? What happens if one of these probabilities is 0?
The whole thing becomes 0.
The whole thing becomes 0 because you're taking products, which means play tennis will be 0. The posterior becomes 0. Probability of play tennis, the prediction says this value should be 0. Right? So, because P of y given x is proportional to P of x given y times P of y, if this is equal to 0, this thing becomes 0. And let's say that on the other side also, when I say other side, this is, let's say P of y equals 1. Let's say for P of y equals 0 also, one of these features never showed up, which means that also becomes 0. But we know that these are probabilities, so somehow 0 plus 0 should add up to 1. Do you see the problem? Okay, how do we fix it? How do we account for events that never showed up in the training set?
Threshold of some probability that it should be greater than this, then only consider it part of the product.
That's one way of doing it, by saying that if you basically do not consider zeros when you're taking the product, but that actually changes the distribution, that introduces some additional complications. It turns out there's an unbelievably simple strategy here. You remember we were counting, right? We were building up all these counts. How do you start counting? You start counting by saying that the number of things that you've seen so far is 0. Then when you see the first one, the number of things that you see so far is 1. See the second one, the number of things seen so far is 2. So your counter starts with a 0. Instead, you start your counter with a 1. You basically make an assumption that you have seen every event at least once. This is called smoothing. Or it doesn't have to start with a 1. It can start with a 0.0001, some small number. So you add small fake counts to your counters, and you just build your counts again. This idea of introducing additional observations that are actually not seen before is called smoothing. If you start your counter with 1, it's called add 1 smoothing. You just add one observation that did not exist in the data. You basically assume that there are no zeros, everything gets increased by 1. So, which means that you will have no zeros in your probabilities. This seems like a hack, right? You pretend that you hallucinate. Basically, changing that counts to 1 is saying that you are hallucinating examples. You are hallucinating that there is this example that never existed. It turns out there's a very clean Bayesian interpretation of this. Introducing counts is actually a way of adding a prior probability over your probability distributions. It's a way of introducing background knowledge. You're saying that I know for a fact that these 0 events should not happen. So I'm going to add a prior distribution and everything goes. So basically, a way to avoid zeros is to go from maximum likelihood learning to maximum a posteriori learning. Let's just work out an example of how naive-based classifier might be used in practice, because this is something that I think you should understand extremely well. Let's say your goal is to build a spam detector. Your inputs are text documents, and your labels, it's basically binary, spam or not spam, and your goal is to learn a function that can predict one of these two labels. How do you represent documents? How do you represent? So the first question is, what are your feature vectors? Can someone give me ideas for feature vectors?
Number of misspellings.
Number of misspellings. 2 more and yes.
Number of fully capitalized words.
Number of fully capitalized words. Another one. Someone who's not spoken so far. Someone who's never spoken in the entire semester so far. I mean, to me, not to each other.
Maybe number of images.
I've heard your voice before, but I'll take that answer. The number of images. You know, you missed the simplest possible answer, which is you take the English dictionary. You don't take the English dictionary. You take the entire email, you break it down into words, and you have indicators for every word. Is the word the in the email? So if I want to represent this as in the feature, so you have an indicator for the word instance. Is the word instance present in the email? Is the word space present in the email, in the document? Is the word text present in the document? Is the word document present in the document? So you have a feature vector with 4 entries which are all ones, and everything else, for every other possible string that can exist, the value is 0. Those are called indicator features for the words. Okay? Anyway, it doesn't matter. Let's say we have these features. How do you estimate the probabilities for the naive-based classifier? What did we just do? You just count. It turns out, for most of the features that you guys mentioned, the features were all not Boolean. They were all number of this and number of that. Which means your probability distributions that you will use cannot be Bernoulli trials. They cannot be just coin tosses, because coin tosses don't give you a number. So they have to be something else. You might make something like a Poisson distribution, for example. But if I had to take the features that I talked about, every feature is the word something present in the thing. It's all either it's 0 or a 1. So this counting idea just works. Once you have the features, the learning is simple. You need to learn these 2 sets of probabilities. And if you have those 2 sets of probabilities, the decision is trivial. I keep saying things are easy because actually this is easy. I know people who have actually written naive-based classifiers on plane trips, despite the fact that they are sitting in an airplane. You can build a spam detector from end to end if you have the data within an hour. The prediction is simply you just, the naive-based prediction given an input features vector to decide whether something is spam or not spam. You find the value of these probabilities for both these things, spam and not spam, and you take the label that has a higher probability. Alright, so you can represent the documents, and once you have the labeled examples, the goal of the naive-based, the task is now to learn. The priors, the probability that an email is spam, before you even see any input is simply count the number of spam emails, divide by the number of documents that you have. If we use the features that I spoke about, which was every word gets an indicator, whether it's present in the email or not, learning is fairly trivial. You count the number of times the word occurs in spam emails. So to learn the probability of a word given that the email is spam, you count the number of times the word occurs in a spam email, and you add 1. Why do I add 1 here? I don't like zeros. So basically, it's the smoothing. The things that are added are the smoothing terms. If basically both the numerator and the denominator here are 0, then these probabilities will be 1 over the size of the vocabulary. Yes? Okay. Oh, vocabulary is the number of words that you have. Because you are adding 1 for every word. So this is basically the sum of all these ones that add up. Because it has to be normalized. Okay. Those are for Boolean features. If you have continuous features, then you basically change the whole story. Everything changes because you can no longer, you don't change the whole story. Actually, you just change the part where you make an assumption about the functional form of the probability distribution. You can no longer have point tosses. You can't have Bernoulli trials. Instead, you can use probability distributions over real values. For example, I think one of your homework questions is kind of probably pushing you in this direction. You could ask, maybe the features are drawn from Gaussian distributions, from normal distributions on the real line. Each feature is drawn from a different Gaussian distribution, and the Gaussian is completely defined by the mean and the standard deviation. So learning the probable naive-based classifier is basically learning the mean and the standard deviation of all these Gaussians. You no longer have one coin toss for the prior and d of them, 2d of them, one for each case, whether the label is 1 or 0. Instead, you have one coin toss, again, label is 1 or 0, and if it's 1, you have d Gaussians. 1 for each feature. If it's 0, you have d Gaussians. Alright, and you should derive the maximum likelihood estimate in this case. It's a very useful exercise. And it turns out, in this case also, the classifier is a linear classifier. The decision boundary is a linear classifier. Alright, so let me wind up this discussion of naive Bayes. The naive Bayes classifier is entirely defined by its extremely strong independence assumption. Every feature is conditionally independent of all other features given the label. We saw how maximum likelihood learning can be derived in the naive Bayes setting. Learning, the derivation might actually be a bit of a mouthful because you have to work through all these somewhat messy algebra, but the final result is actually quite intuitive, and learning is very simple. What we just saw was for Boolean features. It also generalizes to real valued features. We can predict. Okay, this is prediction via map, which simply says predict the label that has the highest probability. Again, it also generalizes beyond binary classification. It turns out because you can just predict labels that if you have multi-class, you just enumerate all the classes, find the probability of that class for each given the input features, and pick the one that has the highest. If you do naive Bayes without smoothing, at any point, I'll find you and I'll scream at you. Never ever learn probability distributions without smoothing. Because you will end up with zeros, and in fact, as an exercise, do it just to convince yourself it's not a good idea. The other thing to remember with naive Bayes is the independence assumptions are strong. They may not be valid, but it kind of works in real life. And effectively, what we are doing is just a twisted way of learning a linear classifier. Any questions about any of this stuff? One of the things about probabilistic classifiers is generally there's a lot of very boring algebra involved. But actually there are a small number of fundamental principles that permeate across all of these ideas, across all these things. The idea of maximum a posteriori prediction, the idea of maximum likelihood learning, the idea of maximum likelihood learning. The idea of maximum a posteriori prediction, the maximum likelihood learning, and maximum a posteriori learning, map learning and MLE. These three things permeate across all three things, or across probabilistic classifiers. Once you get into this framework, then you also have to make a functional assumption about the functional forms of these probability distributions and glue them together. You basically have a recipe for building probabilistic classifiers. You pick a function that represents a probability. You decide, do you want to do maximum likelihood learning or maximum a posteriori learning? Based on that, you have to, it will automatically give you some, an objective, provided you take the log likelihood or the log posterior. And after that, learning becomes basically solving that optimization problem. This might have been one of the few cases where the optimization problem is actually entirely solvable on paper. We don't need an algorithm because I could take the derivative and set it to 0, you get the closed form answer. But in practice, for example, for logistic regression, which we're going to start now, that's not going to work. Okay, let me step up to the we have question.
Sir, posteriority,
Posterior
posterior is nothing but likelihood plus prior
times prior.
times the prior.
Yes.
So basically, isn't it the same thing to maximize our?
No, the prior is actually not quite. It changes the search landscape. The maximum a posteriori learning will change. In some sense, the maximum a posteriori learning will change the sets of functions that you are considering in the same way. Imagine support vector machines with and without a regularizer. If you don't have a regularizer, it's a different function that you're learning, right? It's a similar sort of a concept. The prior probability over the classifiers effectively says, in the absence of any data, what classifier would you learn? And different values of different ways of defining the prior probability can give you different classifiers. We'll see a concrete example of this when we do logistic regression. Alright, let me step up the abstractness of this a bit and go to one of the most important concepts that exists in machine learning. It's the difference between discriminative and generative models. For most of the semester, we saw the following setting. We saw this idea of you're given a data set, and this data set consists of pairs of instances and labels, and there is a fixed, probably unknown distribution over the cross product of x and y. Actually, what we saw was we assumed that there was a fixed distribution over the instance space and there was a fixed function. And examples were drawn from the instance space and the function was applied. Here I am saying there's actually a fixed distribution over the pair x, y. You should think about whether these things are different. But let's for now assume that we have some fixed probability distribution over P of x, y. Okay? And from this distribution, examples are sampled. You have this distribution over x, y, and there's a, points are sampled from this probability distribution, a finite number of them, and that is presented to you as a data set. We've been calling that S. And the job of learning is to find a hypothesis space, define a loss function over this entire hypothesis space, and find a hypothesis that minimizes loss. Maybe there's some regularization involved. And the kind of guarantees that we saw in PAC and other things is that if we find an algorithm that minimizes the loss on observed data, then the learning theory will guarantee that in the future, up to some margin of error, your classifier will be okay. That's basically like a rough summary of the semester so far. Now, one way of characterizing these, another way of thinking about classifiers is we are learning functions that make predictions. I don't care about all these probabilities and stuff. All I want is a function that looks at many examples, combination of positive and negative, and you discover the function, the prediction function that classifies an example as positive or negative. In other words, we want a function h that takes an example x and produces a label y. In order to do that, it turns out that learning this function is conceptually very similar to learning learning this probability distribution, learning a function that can produce the probability of y given x. In this function, it's important to note that the value of x is fixed. So, for a particular function, a particular input x, we are estimating the probability that the label takes a certain value y. Okay. A completely different way of thinking about it is something that we just saw with the naive Bayes classifier. I want to predict the probability of y given x. But Bayes' rule tells me that this is actually proportional to probability of x given y times the probability of y. So instead of learning the prediction rule in the generative model, we learn the story of the data. We learn how are these examples created. We learn p of x given y and p of y. And then at prediction time, we turn them around and use the Bayes rule to predict p of y given x. I'm not learning p of y given x directly. Instead, I'm learning two other functions that tell me how to construct this p of y given x. Let's think about these. This is actually a subtle difference that may not jump out. So let me try to give you an example. In the naive Bayes model, once the learning is done, I want to predict the label for each example. But at the time of learning, I'm first tossing a coin with a bias, the p of y. And based on the value of this coin toss, I'm creating each feature from this distribution, p of x1 given y, x2 given y, and so on, all the way to p of xd given y. Think of these as buttons that I press to get an observation. Once all these buttons are pressed, I get a full observation. So the complete model is defined using all these probabilities. So effectively, in order to predict the label, I'm telling you how I believe the data was generated. The data is actually this complete example, this combination of x and y. In other words, in a generative model, you explicitly learn the joint distribution, p of x comma y, this pair of x, y, and at prediction time, we just marginalize out x. In other words, we're using the capacity of the classifier to model both inputs and outputs of the prediction problem. Examples of generative models are naive Bayes. You might have heard of something called the hidden Markov model, and topic models are generative models. A discriminative model says, you know what, I really don't care about how features are generated. All I want is a predictive rule. So all I'm going to do is learn p of y given x. I'm just going to directly characterize the decision boundary. I only want functions that make decisions at the end. So I'm not going to use the capacity of the classifier to characterize inputs, because I'm never going to be asked to, what the probability of observing this feature is. I don't need to expend the capacity, the representative capacity of a classifier to model how inputs are distributed, because inputs are always going to be given to me. All I want is to learn to predict the outputs. So these are we've seen examples of this before. We will see more of this, at least one more of this. The logistic regression classifier is a discriminative model, support vector machines, and all those things are also discriminative. Effectively, we are directly characterizing the decision boundary. If you, for example, have a bunch of examples of this kind, red is all of these are negative, let's say all of these are positive. A generative model will not only try to characterize this entire, all the clusters that you see. Generative model will expend capacity to learn that there's a cluster here, there's a cluster here, there's a cluster here, there's something like this, and there's a decision boundary. A discriminative model doesn't care. It does not care that the inputs are clustered in these funny ways. It directly tries to learn the decision boundary. In other words, the generative model learns both. If I think of this as a predictor, as an input to output conversion problem, a generative model will learn both the distributions over the inputs and the decision boundary, or will try to learn. And the discriminative model says, I don't care about how the inputs are laid out. I'm just going to learn how the probability of y given x works. In other words, I'm just going to directly learn the decision boundary. And this is an important difference. Generative models have their own strengths and weaknesses. Discriminative models have their own strengths and weaknesses. And I can tell you one strength and one weakness of each. A generative model is often, it turns out some generative models are somewhat simpler to learn, but more importantly, generative models are very easy to extend to the cases when you don't have labeled data. So if you want to do unsupervised learning or semi-supervised learning, if I'm able to generate examples, then I can also try to characterize regularities over examples and automatically learn. Basically, clustering algorithms fall under that, can be naturally written as using generative models. The weakness of generative model is that because you're expending capacity, representative capacity to model both the inputs and outputs, if you don't care about doing that, it tends to underperform, because some of the parameters are spent, are used to model these kind of input regularities. Discriminative models often tend to be the state-of-the-art classifiers when you want this kind of, I have inputs, I want to convert output. If you explicitly want to convert input to outputs. So discriminative models tend to be much better for that kind of a thing because of exactly the reason I just mentioned. On the other hand, the discriminative models are somewhat more difficult to work with when you have unsupervised or semi-supervised learning. So coming up next, I'm going to tell you a little bit more about generative and discriminative models. It turns out the Naïve-based classifier that we just saw is a generative model, and logistic regression can be interpreted as its discriminative counterpart. It has the same decision rule, except the logistic regression is a discriminative variant of the Naïve-based classifier. But what we'll see next is how to do maximum a posteriori learning for logistic regression. And in a very nice way to round up this discussion, it turns out logistic regression can be viewed as without a probabilistic lens at all. Logistic regression is also can be seen as within the loss minimization framework that we just saw maybe a few weeks back, without even making any assumptions about probability distributions. And within that, that perspective is actually very important, because that idea is what leads to a lot of work that, ways of building neural networks that we'll get to after that. Any questions about generative and discriminative models? Yeah.
So pack learning has any relation?
Pack learning is a way of asking, is my classifier good? Pack learning is a theory that characterizes how good is your classifier. Typically, all the stuff that we saw for pack learning was in the context of discriminative models, right? Because we have functions that take x to y. We don't care about the actual p of x. That said, remember that pack learning did not even care about what your actual learning algorithm or anything was. If you could characterize the hypothesis space, pack learning is well defined. Right? All the guarantees just follow from that. So if you can write down the hypothesis space, everything's done. Alright, in the 5 minutes that are left, I'm going to give a quick introduction to logistic regression, and then in the next lecture, which is next week, we're going to talk about logistic regression. So we've seen linear classifiers, we've seen learning as loss minimization, we've seen Bayesian learning criteria, map and maximum likelihood, and we've seen the Naïve-based classifier. Turns out logistic regression is an interesting synthesis of all these 4 ideas. So let me just define what logistic regression is. We have binary classification, same stuff that we saw all the time before. You have inputs which are feature vectors and labels plus and minus, and you have a bunch of examples. Instead of predicting and given the lack of time, I'm just going to set up the intuition and we'll actually get to the formal stuff later. So far we've been predicting the label y, except in the Naïve-based setting where we predicted the probability of y being 1. But for Naïve-based, what we did was we said we're going to predict the probability of y equals 1 given x. Instead of learning this function, we tried to learn p of x given y and p of y. The starting point of logistic regression is, what if we directly learn this function p of y equals 1 given x? The original problem that we cared about was a classification problem, which was, I have a d-dimensional vector, I need to predict a +1 or a -1. But this function p is real value. If I want to directly learn that function, I have to learn a real valued function, right? This is a probability is a real valued function. In this case, it's a function, you can think of it as a function that takes values between 0 and 1. So the new problem, if I directly want to learn the probability of y equals 1 given x, the new problem is a regression problem, where the inputs are these d-dimensional vectors, and the output is a number between 0 and 1. So effectively, I have converted this problem of learning a classifier into a regression problem. And now I need to think about what is a good hypothesis space. There are many hypothesis spaces possible, but the thing to keep in mind is we need, what is the characteristic of this hypothesis space? The characteristic of this hypothesis space is we need functions that can take d-dimensional vectors and produce numbers between 0 and 1. You cannot do linear regression, because linear regression will not produce numbers between 0 and 1. And what logistic regression says is we're going to assume that this is the hypothesis space. We're going to take all functions which satisfy this functional form. You take an example x, the function is completely defined by a weight vector w. You've given an example, I take the example, I take a dot product of that example with the weight vector, and then I pass it through what is called a sigmoid. This sigmoid function which has this form, 1 over 1 plus e power minus that number. You take a linear function and you compose it with a sigmoid, and you have to convince yourself that this can only take values between 0 and 1, and this will be our hypothesis space. Alright, let's stop now. We'll stop an entire minute early because of the holidays that are coming up.
You're so kind.
I know, I try. So, alright, I'll see you all next Tuesday. Have a happy holiday.
I